All right, so we're continuing with this idea of equilibrium. And I think my other class found today good because it was this nice putting the quantitative stuff together with the concept. So it really reinforces the concept, but then also gets you into some problem solving. So this is kind of usually my favorite day in chapters where we get to pull it together. And I think it starts to really make a lot more sense. Okay? So we are going to start by using the equilibrium expression that we talked about, but using it with quantitative values. So when we approach these next two problems, we're going to take like 3 basic steps to figure out how to do this. And this is true of any of the problems. We're always going to want to start by writing K symbolically. That probably was only one L there. So in this instance, what I mean by that is we say K is equal to products raised to their coefficients over reactants raised to their coefficients. That's what I mean. Write it symbolically. Then the second thing in the more simple problems is going to be plug in any values that you have for these and solve for whatever they're looking for. It's like you're basically writing out the equation you're going to use and then finding which variable is unknown. So before we start, let's just read the question together and then I'll let you guys solve it. So it talks about temperature in this problem. It says at a given temperature, and then later down here it says what's the value of the equilibrium constant for this reaction at this temperature. K is temperature dependent, meaning that if you change the temperature, the K value is going to change. We're never going to do calculations that involve changes in temperature. So you don't have to worry about that. The questions just often will say that to like reassure you, we're not doing a change in temperature here. We're looking for at the same temperature, what is the K or what is the concentration, okay? So even though they talk about it, you don't have to worry about it. So then it says at this given temperature, a 2.5 molar sample of HBr is allowed to decompose until the reaction reaches equilibrium. So let's just kind of jot down. We're gonna do more than we need to. Like if you were solving this problem, you don't need to go through all these steps, but I wanna use it as a way to reinforce the concept. So I'm going to write down this little table that we're going to start using at the end of today and going into Wednesday. We call it an ICE table. It stands for initial, change, and equilibrium. And that's squeezing it in way too close, but here, maybe I'll put the initial above it. So usually we just write it below the reaction. I'm going to write initial above here, though, so I have room. Okay, so it says a 2.5 molar sample of HBr is allowed to decompose. Okay, so I'm starting initially with 2.5 molar. Do I have any H2 or Br2? It doesn't say that. So it just is saying you're starting with HBr and it decomposes. So I'm going to go ahead and write 0 for both of the reactants because as far as I can tell, they just told me I started with HBr. Then the thing reacted. We don't know how much exactly reacted. But in the end, it tells us that it achieves equilibrium, and once we get to equilibrium, these are the concentrations. So we need to really clearly in our head separate initial concentrations from equilibrium concentrations. So remember, we have this whole idea of balance points. So maybe on this one, the balance point is like here-ish, okay? When we started, though, it was all reactants, no products. So we're saying what changed. We're not going to look at the change in detail, or maybe we will just for practice, but something changed from here. The reaction proceeded and then it stopped at this point. And now at the balance point, these are the concentrations. So to keep track of all of that, I'm going to write down those concentrations under each chemical species in this table, under equilibrium. So 0.50, 0.450, 1.03, and 1.03. Okay, like I said, you won't necessarily have to have this level of detail for a question like this, but I want you to understand what's going on. So 2.5 molar got reacted, still 0.45 was left over, but some of it got used up and made 1.03 of each of the reactants, okay? So started like this, all the reactants, zero product, and then it went like this and stopped there. So still some reactant left over, 0.45 molar and 1.03 of both of the reactants, okay? Well, if we know the equilibrium concentrations and we know what the K expression is, we can now solve for K by just plugging those values in, and that's what it wants you to do. So this whole table thing, that was just so we can talk through it. But really, the question, all you need to do is plug in the values for K and determine, into the K expression rather, and determine what K is. Okay, so go ahead and do that. Figure out what the equilibrium constant is for this reaction, and then we can talk a little bit about product favored versus reactant favored. Okay, so 5.24 is the equilibrium constant. So if you know the equilibrium values, you can really quickly determine the equilibrium constant. Or in the next problem, we're going to know the equilibrium constant and find an unknown value for one of those reactants or products. So what does this value tell us? 5.24. So 1 is where they're basically equal products and reactants. And 5.24 is like a little bit on the product side, slightly product favored. But remember, 5.24 is like a ratio, 5, let's call it 5 products for every 1 reactant. So it doesn't mean that there's no reactant. In fact, we know there is some, right? There's 0.450. So some reactant remains, but it's more on the product side, okay? So if you were given the equilibrium constant, you have a feel for what the ratio should be. If you're given the equilibrium values here, you can actually determine K. And then this stuff up here was just so that you can visualize a little bit what's happening as the reaction proceeds. So let me just hit this point up here, this whole idea of the ICE table, because we're going to introduce it here, and then at the very end of class, we're going to look at one that's kind of more formal, how we would use this. So in this one, we really have all the information. So it started as 2.5, and it went down to 0.45, right? So what we're saying is 0.45, okay. So I should have done that in my head. So 2.05 molar got used up, right? Because that's how we get from 2.5 to 0.45, is we use up a certain amount. And then we made 0.103. So you could actually write in there what those changes are. You could say minus 2.05 plus 1.03 plus 1.03. The changes are always going to be minus on the side where you're using up that thing. So on the reactant side in this case, because you're making product, and then positive on the side where you're making it. You can kind of think of it as the initial plus or minus that change is equal to the equilibrium. Okay, you're saying how it changed and then what it ends up as. So yes, the first step is always going to be write K symbolically. In most of the other problems, if they're not super straightforward, you're going to end up writing one of these ICE tables just to like organize your information. Here, it's not really necessary, because as long as you acknowledge that this number, we don't actually use it in the calculation because it's not equilibrium. We only want these equilibrium amounts because it's asking us for the equilibrium constant. So really, to do this problem, we did not need to know the 2.5 molar. Interesting information, but not pertinent to the question. Okay, let's have you guys do another one of these. And I won't give an introduction to this since we talked about the other plenty. So I'll just give it maybe 3 minutes before I start working it up there. But you guys take the time, read the question, figure out what it's asking for. Same general approach that we did before. Don't worry about the ICE table thing. That was just me introducing it. Don't do anything with that. Just write the K expression, solve for what you're looking for. sure what happened there. So I'll start working it up here, and I'm going to start by writing the K expression and then plugging in what I do know to solve for what I don't know. Oh, and I just realized not concentration, pressures here, because this is a KP. Okay, so you should have a pressure for the phosgene, COCl2, of 0.150 atmospheres. So these problems where these are the simplest ones, you have the K expression and you have equilibrium concentrations, okay? You may be missing the K, you may be missing one of the equilibrium concentrations like in this one, but it's very important to differentiate between, like here, these are pressures at equilibrium, okay? They are not starting values, they are not initial. In that previous question, it was important to understand that too. These were the equilibrium values. This was an initial value. It was before it had gotten to its balance point, okay? Because you are only allowed to plug in equilibrium values into the K expression. That's the whole point. That's the concentrations once it's achieved that balance point, not when you first put it in the container. Because like in this one, it says, carbon monoxide and chlorine gas are allowed to react. So you have to first let them react and then get to the balance point. In this instance, the balance point is slightly reactant favored. So that's one thing we can say about this. Not a huge favor towards reactants, but a reactant favored. One would be they're pretty much the same, but we're saying it's 0.15. So it's like this a little bit more reactants. But when we start, it's all reactants and no products. We need to allow it to achieve its balance point, then we can plug that into the K expression, okay? That ratio, when the pressures are at equilibrium, that's what's equal to that K value, okay? So that's probably the first tip, is be really clear, label what's initial versus what's equilibrium. And this whole idea of the ICE table that we're getting to, that's what's going to help you to do that, to get used to summarizing which concentrations are which so you don't get them mixed up. In one where you're only really given equilibrium concentrations, or at least you're given enough, you can just go ahead and write the K, plug the values in as long as they're equilibrium values, and solve. Okay, any clarifications about those two that we just did? Okay, so the next thing we need to deal with is lots of times it tells us which direction the reaction's proceeding. Most of the time you stick reactants in, you let them get to their balance point, to equilibrium, and then you solve something. In this case, that was what it said, carbon monoxide and chlorine gas. You started with the reactants, you proceeded to make products in order to get to the balance point. On the previous one, you started with reactants. You started with HBr, it reacted or decomposed and formed the products. Okay, so I want you to go to this next page. And in this one, this reaction here, these that are listed here are initial amounts. And what we want to talk about is which direction does the reaction proceed? Okay? The first one is similar to the other two problems. We stick reactants in, there's no products there. So, of course, no matter what the K is, we need to make some products. So we're going to say the reaction proceeds from right to left, just like we're used to, the reactants making products. But what about if we have something like the middle one? What about if we've got this reaction, it has a particular K, what about if we stick the product in a container? Is it just going to sit there? Like, oh, I already am a product, I already made what I'm supposed to make. No, because there's a balance point for this reaction. It's 50, which is product favored, right? That 50 means it should be 50 parts product for every 1 part reactant. So it's very much product, but not zero reactant, okay? So if I actually stick HI in a container, it's not going to just sit there. It's going to react backwards and revert to some of the reactants to achieve that balance point. Okay, so the reaction will actually proceed in the opposite direction from products to reactants and make some of those reactants. And that's actually true anytime one of the species, one of the chemicals is zero. Like we could add, in the last example, we could add some of the product and one of the reactants. But if we don't have any of this reactant, I guarantee you the reaction has to proceed towards the reactants to make some of that I2. So you kind of have to shift your thinking a little bit, because for probably all of chemistry, you've always thought of reactants turn into products, reactants turn into products. Well, that's true if the K is huge and it only makes products. But when you have a K that is kind of in this middle range, let's say roughly 100 or 1,000 down to not even 100 or 1,000, like, I don't know, even like in the millions, 1,000,000 to 1 ratio, there's still some reactant there. Just like if we have a really small one, like 10 to the -9th, there's still a little bit of product and lots of reactant left over, okay? We can't ignore those small amounts because they do have an effect sometimes. After this chapter, we're gonna go, the rest of the semester we'll spend on acids and bases. And if you guys are at all familiar with acids and bases in the body or in any kind of biological system, it's a big deal if you have small amounts of an acid. And so the equilibrium constants of an acid are important even if they're really, really small. We'll see acids with like 1 times 10 to the negative 5th or 1 times 10 to the negative 10th, and they still have an effect even though they're super, super reactant favored and not very much of their product is made. Okay? So takeaway from this slide is that anytime you have 0 of one of the chemicals, you're always going to have the reaction proceed to whichever direction will make more of that chemical, the one that's 0. So in the first one, I've got to make some product. In the second one, I'm going to go backwards and make some reactant. And in the third one, even though I have some of this reactant, because this one's 0, I also have to go backwards and make a little bit of that. And that's true whether the K is product or reactant favored, okay? So I'll write that as well. True of reactant favored as well. Yeah.
So I think it tends to be product favored if it's more in the numerator, right?
Yes, yeah. So the bigger the K value means more product is made. And you're right, if we're looking at it as a numerator and denominator, then yes, the product favored means that the numerator is bigger, denominator is smaller.
Typically, if it's reactants, it's like kind of decimal on top.
Right, exactly. So it would be some sort of a less than 1 decimal. You can think of that as a small amount on top and 1 on the bottom.
Now, is it like always product of a reactant, or is it
Yes.
some exception?
Yeah, K is always product of reactants. Keep in mind that even though we're talking about these reacting both ways, we still always think of this as products and this as reactants. Even though, like in this example, we're saying this reacts to form that, we don't start calling that products.
So even though the arrows, it doesn't really affect
Yeah.
like what you're...
Right. Always consider the thing on the left to be reactants and the thing on the right to be products. And when you write the K expression, so like in this example, K would be products, HI, squared over reactants. And that ratio should be 50. Or a way you can think of that is 50 to 1. So 50 products to every 1 reactants.
Yeah.
Yep. Good?
Yeah.
Okay.
That was important to clarify.
Yeah, good. I'm glad. I
Yeah.
can never know what exactly needs clarification until you guys
Yeah.
ask. So, okay. Scratch out this 1. That was a typo before we start anything on this slide. Okay. What about if there's some of everything? So in each of these examples, maybe we stuck all of this stuff in a container, H2, I2, and HI, or maybe the reaction proceeded a little bit, but we don't know yet if it's at equilibrium. Okay, so it could be any kind of reason for why we have some of each of the things, but we don't know yet if it's at equilibrium, and if it's not at equilibrium, which direction is the reaction going to go to get to equilibrium? Okay? So before I actually introduce this concept of Q, let's just look at, is this thing at equilibrium, the first one? So if it's at equilibrium, the ratio HI squared over H2 times I2, that should be equal to 50, right? If it's at equilibrium. So go ahead and plug those numbers in and see if it's at 50. So at the very least, that'll tell you, is it at equilibrium yet or not? Tell me when somebody has a number for that. Do you have one? No. Come on. Yeah, it's 1. So it's 0.5 squared over 0.5 times 0.5. So it's 1. So it's not 50, right? So this is not at equilibrium yet. Not at equilibrium. So then the question is, which way is the reaction going to go to get to equilibrium? So if it's currently a ratio of 1 to 1, and we want it to be a ratio of 50 to 1, that means we need to make more products, right? We have to get that top number to be significantly bigger. So watch my little balance point thing. This is where we're at, 1 to 1. We want it to be 50 to 1. So what does that mean? We got to make products and use up reactants. The way we do that is proceed towards the products. The reactants react, so they get used up, they go down. So like the denominator would be going down then. And we make products, so the numerator would be going up. So what we do, we're going to do this every time that we're not sure which way the reaction goes. We're going to plug the numbers into the ratio that we use to find the K expression. But just so we don't get confused, we're going to give it a different letter. We call it Q. It just means we don't know if we're at equilibrium, so we don't want to say K is equal to that. We're going to say it's Q. So it's still the same ratio as K. Products raised to their coefficients over reactants raised to their coefficients. But we're just solving for what it is. So in this case, we got 1. And then we're looking at it and saying, okay, it is 1 currently. Does it need to go towards the products or go towards the reactants so that Q achieves the K? We're trying to get it to be 50, right? 1 needs to turn into 50. So how do we turn 1 into 50? We drop the denominator and increase the numerator, or go towards products. So this is summarized down here. If Q is less than K, the reaction must go to the right, and I'll add to that, form products. Okay, proceeds to the right means it makes products, uses up reactants. So a little trick, just because everyone always likes these little reminders in case you get stressed during a test. Maybe it's easier to remember the thing instead of the reminder, but whatever. You have to do it in the order Q. If Q is what, then K. If Q is less than K, the arrow, whatever the way the less than greater than sign is pointing, that's opposite the reaction needs to go. Okay? So if Q is less than K, the reaction goes this way, towards the right. Okay, do the next 2, because the opposite is going to be true as well. If Q is greater than K, then the reaction will go to the left. So solve the next 2. find out what the value of K is, and predict which direction the reaction needs to proceed.
Is that one in the second column incorrect?
Yeah, the 1 shouldn't be there. Yeah,
Oh, okay.
that was a typo. Thanks. Okay, so I'll plug these in. You can check your work as you get it. Okay, so with these numbers, both of them are larger than the K. One is hugely larger than the K. One is just slightly larger. But what that means is the ratio is off with a little bit too much product. We need to bring it, well, a little bit for the third one, way too much for the second one, right? We need to bring the product down and make some reactant in the process. So bring the top number down, bring the bottom number up, which means we need to proceed towards the reactant. So if Q is greater than K, the reaction goes to the left or towards the reactants. And this is going to be really important when we start to do more complicated problems and we're trying to define that change. We need to know, are we changing, like using up some of this stuff and making more of that? Or are we using up some of this and making more of that? Okay? So in every reaction, you either need to look and say, is one of them 0? Okay, I'm going to go to make that. Or if none of them are 0, you have to figure out what the Q is and decide which direction is that reaction going to proceed. And if you happen to get that it's equal to the K, that means it's already at equilibrium. So it's done. All right, let's do one more of these. So these are, I'm going to say current concentrations. We don't know if it's at equilibrium, or we don't know which way it would have to shift, but you need to find the Q and then determine, based on Q versus K, which direction the reaction is going to proceed. All right, so 0.25 and the K is 0.1. So Q is greater than K, meaning we need to drop the products a little bit and raise the reactants a little bit, or the reaction goes in the reverse direction. All right, so let's just look at one more problem. It's like our intro to the next stuff on Wednesday. I want you to see like how these ice tables might work. So this question would say in words, you know, you've got 0.5 molar CO and 1 molar H2 in a container. They react and form an equilibrium concentration for CO of 0.15. Determine the K expression. And you're like, how can I determine K if all I know is the equilibrium value of the CO? So you start by summarizing your data in this ice table. And because we know that there's no product to start with, we know the reaction is proceeding towards the product. So the first thing we want to do is we're going to define the change in symbols. So some of that CO is going to get used up, right? And some of the H2 is going to get used up. The amount that will get used up is a 1-to-2 ratio, right? If you look at the balanced equation, there's a 1 on the CO and a 2 on the H2. So I don't know exactly how much at this point, but some, so I'm going to say some X, some amount is going to get used up. It's minus because it's getting used up. But then for H2, I'm going to have twice that amount of X because I know from the balanced equation, it's a 1-to-2 ratio. And then also from the balanced equation, I know that I'll make that same amount the 1 ratio of H3OH. So I'm going to say plus that amount for CH3OH. And these steps are all summarized at the top of the next or the previous page. You write down the K expression symbolically. We haven't done that yet, but you summarize your data in an ICE table. You define the change, meaning like you need to know which side is minus, which is getting rid of, and which side is making more of. And then you try to synthesize the data and figure out how you can get to it. Now, as I mentioned before, think of this line as an equals line, okay? The start minus the x is going to be equal to this, okay? Well, 0.5 minus some value equals 0.15. I can say then that x is equal to 0.35, right? Because if I take 0.5 and I subtract 0.35, I get 0.5. So I have just figured out what x is, meaning I can go in and plug that x in here and figure out what these equilibrium concentrations are, and then I could plug it into my K expression. And once I do that, then I would have the value of K. All right, so the ICE table is super important for like processing all of your information. So we won't finish it right now because it's 50, but you could go in and plug that in, maybe do it on your own or at the beginning of class or something. So what I would recommend is spend some time tomorrow, do some of the simpler problems in the homework, and maybe even take a shot at something that requires an ICE table. And it'll just give you a good warm-up, because this is the more difficult stuff. Like Wednesday is going to be the most difficult type of material for the chapter. So we'll want to go through lots of those. Okay? Yeah.
Is our test next week now? Instead of Friday?
Did it say it's Friday? I haven't updated the schedule since we messed up the schedule. So yes, it's definitely next week. So we'll finish the chapter on Friday, which means Monday will be a review, which means Wednesday will be the test. So I will make a note to update that.
Can you go back to the previous slide?
Yeah. This one?
Yeah.
Okay.
So you take a picture.
Yeah, that's fine.